Okay, our next talk is about server routing traffic engineering with auto bandwidth. The person who's just asking a question is the speaker, so if Arista wants to come back and ask a question at the end, feel free. So this is Dmytro Shypovalov. He's actually joining us all the way from Ireland, so please welcome to the stage.
All right, hello everyone. My name is Dmytro. I'm a developer of Traffic Dictator. For those who never heard of it, it's a PCE, Path Computation Element for segment routing, which I try to make it based on open standards and work with all vendors. So in theory, you should be able to run it in any network. But this specific talk is about my prototype of auto bandwidth implementation with segment routing, which there is no standard for it, and really there is no well understood and common way to do it. So that's just a prototype. So a bit of background: what is auto bandwidth? Auto bandwidth with RSVP traffic engineering is not a new thing. It has been there for a while. With resource reservation protocol, RSVP, you can signal a bandwidth reservation per LSP, this way you can assign static bandwidth reservation, but a router can also measure the actual LSP traffic utilization and adjust LSP signaling based on that actual data. And it can adjust it periodically with whatever interval you configured, like a couple of hours, or react on sudden traffic changes. So RSVP-TE unfortunately has a few problems, even though it generally works fine, but it doesn't scale very well, especially in very large networks. You have a lot of LSP. It doesn't interoperate very well in multi-vendor networks. There are lots of issues, and also because it's really complex protocol, not that many vendors actually have a good implementation of RSVP-TE. Another problem when you have a distributed traffic engineering with RSVP, there is no deterministic routing. So every time the network reoptimizes, you can get different results and traffic will flow differently. Also, auto bandwidth pilot can quite well react on changing traffic patterns, but it doesn't react well on changing BGP destinations. So when you BGP reroutes and traffic shifts from router 1 to router 2. Also, with traditional MPLS-TE, there is no standard mechanism to map different services on the same router to different LSP. There are some workarounds that you can do with multiple loopbacks, but there is no standard method. And also, there is a management issue. If you add a new router to the network, you need to configure LSPs on all routers in the network. So a lot of configuration overhead. So what about segment routing? Segment routing solves a lot of problems that RSVP had, but also adds some new problems which RSVP didn't have. There are a lot of implementation of SR, especially if you are a smaller to mid-size ISP. You don't really have to go to one of the big vendors. You can use some white box vendors, some open source implementations, some virtual routers. There are lots of vendors that support segment routing. And because it's much simpler, there is no signaling, it interoperates reasonably well, much better than RSVP. And there is a standard method how to map services to the LSP using color extended community. Now, what about the caveats with segment routing? Because it's stateless, you cannot do bandwidth reservation, or rather you can, but you need a centralized database provided by PC or controller. But how about if you want to do auto bandwidth? So we need to achieve some kind of feedback loop between the router and the PC. So let's first examine how PC works in segment routing. There is the protocol address family for BGP called BGP link state, and it allows you to redistribute your ISIS or OSPF link state database into a special BGP format and then advertise all the data to the PC so that PC can have a standard way of representing the link state information. It can compute SRT policies, and then it has three standard methods plus some proprietary methods of advertising policies back to the network. One of the methods, which is the best actually, is BGP SRT, RFC9A30. Works very well, scales pretty much infinitely. As we will see later, this is the chosen method I recommend, and it's chosen for this implementation. There is also BGP labeled unicast. It's not really a standard for segment routing. It's a very old protocol, but it works well with legacy routers that don't really support any traffic engineering. And there is PSAP. PSAP is a terrible protocol. Nobody should use PSAP for anything ever. It's a very bad protocol. Very poorly written, bad standards. There are like 50 RFCs and still don't really standardize anything that actually matters. And then, of course, there are all kinds of vendor proprietary, netconf, API, whatever. So how do we implement out of bandwidth with segment routing? There is this RFC 8773 PSAP extensions for LSP out of bandwidth adjustment, and it basically tried to re-implement the RSVPT out of bandwidth, but now with PCE, by achieving a feedback loop between the router and the PCE, so the router can signal the current LSP utilization to the PCE, and PCE can adjust signaling based on that. I don't know if anyone has actually implemented it. And as I already mentioned, PSAP is not really a well-designed protocol. So it's not maybe the best idea to use it. So there is a better approach. There is this new RFC 9857, which covers advertising of segment routing policies with BGP link state. And the idea of that RFC, it adds a new BGP-LS route type, type 5 for SRT policy, and the idea is to improve SRT policy visibility so that if you have a hybrid SRT design, when some policies are configured on the routers and some policies are configured on the PCE, routers and the PCE can all advertise the policies in the same into BGP, so everybody can have the full view of all policies in the network. And that was the idea behind the RFC. But what is of interest for us is the SR bandwidth constraint TLV, which specifies how the router can advertise bandwidth utilization of an LSP into BGP link state. Aside from it, most routers that support segment routing, they also support per LSP counters. And in practice, counters and this new BGP-LS route type, it's everything that we need to implement out the bandwidth. So this is the design of SRT sampler. Sampler is a separate software, separate from PCE, and we will see in a minute why I made this decision to not implement this functionality in the PCE itself. So the sampler uses GNMI to stream counters from the router to the sampler. It's based on adjust interval. The sampler updates bandwidth for each LSP and converts it into the BGP-LS format and advertises this to the PCE via BGP-LS. PCE receives information from the sampler and adjusts LSP bandwidth reservation. And currently, the prototype works with Cisco, Arista, and Juniper implementation, but again, it can be extended to support any other router which supports GNMI and per LSP counters. And going forward, if a router implements the new BGP-LS route type and can advertise the counters directly, then the sampler wouldn't even be needed. We can just have this between the router and the PC without sampler. Also, it still can be beneficial to have a centralized bandwidth database, as we will see later, because when we have a central view, we can run all various analytics and modeling of traffic patterns in the network. So this is an example of sampler configuration. I really just used the industry standard CLI, as most people are familiar with. Configure sampling options. Let's say collect counters every 10 seconds. Adjust policies every 60 seconds and adjust only if the traffic rate changes by 10% from the previous sample. And then there is BGP configuration, telemetry configuration, and so on. And this is the output we'll get. Each SRT LSP is identified by a tuple of 3 values, the headend, endpoint, and color. And we can see the measured bandwidth rate, which is measured from, I think it says, from 6 samples over 50 seconds. And then what do we implement on the PC? The PC really only need to receive this BGPLS type 5 route and then correlate this tuple headend, endpoint, color to the policies that exist on the PCE and map the relevant bandwidth reservation. And this way, out the bandwidth work with segment routing. But it's really not something revolutionary because it just replicates the behavior which existed in RSVP-TE for 20 years ago. So not something very spectacular. But it can get much better. So, SRT mesh templates. It's my solution, which implemented last year in Traffic Dictator. It's a solution to a management plane scalability of traffic engineering. Because I think on the second slide, I mentioned that segment routing scales better than RSVP. That's what everybody says. That concerns control plane, but management plane is the same. You still need to configure LSPs. Mesh templates solve this because you just configure one template per topology, or maybe a couple of templates, and the PCE would automatically generate a lot of LSPs according to your requirement, which is, in my opinion, the correct way to do intent-based networking. Templates are also fully dynamic because when a new router is added to the network, PCE would generate new templates to include those new routers. And you don't need to configure a session, a PSEP or BGP session between PC and each router. You only need to configure one session with a route reflector or maybe 2 sessions for redundancy. And this is how it works. You have a very minimalistic config which says, I want to generate a mesh of LSP from each router in the topology with ID 101 with color 11101. And it specifies constraints, use the admin group, which we call core links. It can also, as we will see later, use different constraints like bandwidth reservations. And the way the LSPs are advertised to the network is using BGP SRT. And in BGP SRT, the PC would set route target in each LSP equal to the BGP router ID of each headend which need to install this LSP. And this way we avoid the need of configuring lots of BGP sessions because everything is advertised to the route reflector and the route reflector distributes routes to all the routers that need them. We can also exclude some routers, like core routers, with an access list. And this is a couple of demos. So a demo, in this network, we have Cisco, Juniper, and Arista routers. And between R3 and R5, we have a link with lower latency, but it has limited bandwidth. And between R4 and R6, we have a link which is, let's say, higher latency. It's less preferred, but it has higher capacity. So how do we route traffic using only blue links, but using the lower latency link, but also avoiding congestion? In this case, we have 3 LSPs that each of them use about 30 gigabit of traffic. So apparently, if you route all the 4 LSPs with 30 gigabit of traffic each over 100G links, there would be a congestion. And in this example, we use out the bandwidth to avoid this. by routing only 3 LSP over the low latency link and the other LSP over the high latency link. And this is a configuration. On the left, you'll see the configuration on the PC. We have a template with admin group constraint and the capacity profile, which just says to use auto bandwidth. And on the right, you see an example of the BGP-LS type 5 route, which maps to the LSP using head and endpoint and SRT color, and it shows the measured bandwidth rate. And on the bottom, you see the output of all policies generated from the template. As you see, there is policy from each headend to each endpoint with the relevant color, and it also shows the measured bandwidth for each LSP. Or rather, because the output is from PCE, it shows the reserved bandwidth, because we receive the bandwidth from the sampler. The second scenario, we have two meshes. We have a high priority but low bandwidth traffic, which is latency sensitive, and we want to route it over the best link with lower latency. And then we have a lower priority LSP mesh with high bandwidth traffic. And this is how we configure it. We configure two meshes with different SRT color, and we configure a higher priority, which in MPLS-TE terminology is a lower numerical value of priority 5. Default priority value is 7. And what happens is that the higher priority policies will be configured first, will be calculated first. They will check the preferred links, and then the lower priority LSPs would take the best effort path. And this is the output. We will see, again, two meshes. Each of them generates about 12 policies, I believe. What about redundancy? Because the solution is based on open standard, pretty much two BGP address families. It's easy to understand because everybody knows BGP. Easy to understand how it fails and how to design redundancy. It's just BGP. SRT is sampler. There is no need to have it redundant, and it would be actually quite difficult to implement redundancy given that we need to write to a centralized database. It's possible, but fairly complex. To avoid any split brain. But also, it's not a critical element. Even if it fails, we can just restart it on a different server with Kubernetes or something or whatever. PC, that's again big misconception a lot of people have. They think, oh, we don't want a centralized controller in our network because what happens if it fails? I think the better way to think about PCE design is more like route reflector design, because it also talks BGP, and there is no need for any proprietary state synchronization. I know that some vendors want to push you some proprietary state sync between their PCE, but I don't think there is any reason for it, aside from selling you expensive software. So you can just configure multiple deploy as many PCs as you want without any state synchronization. On each PC, we configure a different SRT distinguisher so that when they send LSP to the network using BGP SRT, different PC would send you exactly the same LSP but with different distinguisher. So if one PC fails and the route is withdrawn, the router would still have the exact same policy from the other PC. The concept, this design is very similar to MPLS VPN, which also is typically designed with different routers, advertise the same customer route with different distinguisher. And even if there is a catastrophic failure of all PCE, let's say due to software bug, traffic will just follow the shortest path, which can lead to a congestion, but again, it's not a critical failure. The conclusion that it's a simple solution, which is based on open standards. It works with all vendors that support relevant standards. The config is very minimalistic and it's self-updating, so you can just turn it once and forget, which is, in my opinion, how intent-based networking should be, without all the marketing nonsense. The routing state in the network is deterministic because all the LSPs are calculated by the PC, by a centralized PC, and not rather than each router computing for itself. We can also prioritize, like have some real-time traffic having higher priority. There are other things I didn't show in this presentation, like disjoint path, when you can have two LSP meshes, which would be guaranteed to take different links, so disjoint path. BGP SRTE scales very well, because as you all know, BGP for internet routing can carry millions of routes, and here we will never really have billions of SRTE policies, maybe tens of thousands, hundreds of thousands, but not as many. And BGP does it very well. SRTE sampler is just a prototype, and it's an open source, so you can download and play with it. If there is any interest, I will develop it further, of course. Traffic Dictator is not open source, but there is a free version for evaluation available. The next step, so yeah, as I say, this is just a prototype. It is possible to implement much more features on top of this. For example, LSP splicing merging, which is also called container LSP by some vendors. Because we have centralized view, the outer bandwidth has a potential to work much better than RSVP-TE outer bandwidth, such as reacting on BGP destinations. It is possible to freeze the state of outer bandwidth or roll back to a certain point for troubleshooting if you suspect that something went wrong. Because we have a centralized database, we can run various analytics like spot some long-term patterns, see if a certain link needs upgrade, or if we need to, if it would be a good idea to provision a new link between certain routers. And we can actually get the best of both worlds when there is a simple and deterministic algorithm that controls your actual LSP provisioning, but also a centralized database for offline analytics. Because typically with RSVP-TE, you would have either one of those, either the feedback loop, the real-time feedback loop, or a centralized database for offline computations. So yeah, that's it. For now, it's just a prototype, and I'm open to questions or comments or criticism of the solution.
We definitely have time for questions. Don't be shy if you want to ask a question about it. If you want to know more about Traffic Dictator or segment routing, Dmytro knows a lot. I had a beer with him last night, and I feel like he was teaching me so much in just one evening. Yeah, if you could go to the mic. If you don't mind saying your name and stating your affiliation before your question, that'd be great.
My name is Mike Boy. I'm self-affiliated, but I have the opposite of a criticism, which is that this prototype, as you've described it, looks like it is very forgiving to the operator. When you talk about multiple redundancies and the catastrophic, it fails down to just functioning normally. And my experience here is not exceptionally deep, but I do want to point out that forgiving to the operator is not a term I hear associated with BGP very often. And so I'm glad to see that I'm delighted to see a prototype or an effort towards making systems that are, even at this scale, very human accessible. So thank you.
Thank you for the comment. I think, in my opinion, in network software design, there should be some balance between things being simple enough, but also that network engineers can understand how they work. And if something goes wrong, they can troubleshoot, maybe switch off some component. Like in this case, you suspect something goes wrong with outer bandwidth, you can just switch off outer bandwidth and maybe you still SRTE, but without bandwidth reservations. I think there need to be a balance between simplicity and control. But thank you.
Any other questions? Okay, we're good. Thank you, Dmytro.